This video will cover evaluating limits algebraically. Before we jump in to some examples of evaluation, we're going to take advantage of two limits that we know their values for and combine that with a list of rules and be able to determine the value of limits of all polynomial and rational functions. So there are going to be times where we run across a limit that we need to evaluate, and we don't have the aid of a graph to determine that limit, so we need to know how to do it algebraically. The two limits that we are going to utilize is the limit of a constant function as x approaches a. So a constant function is just a horizontal line in our xy plane. So therefore, every time x approaches any value a in that coordinate plane, the limit will always be equal to whatever the value of the constant function is. So that's the first one. The second is the limit of the identity function. The identity function is a function where whatever you plug into that function, the output is whatever you plugged in. Okay, it gives you back what you plugged in, hence the name identity. Therefore, you can expect that the limit as we approach a will be whatever that value we're approaching is, in this case, is a. Okay? So the limit of a constant function at any point is the value of that constant function, and the limit of the identity function along any point is the point in which x is approaching. So now let's jump into some properties of limits, and we'll see how we can use these properties along with those two pre-established limits to determine the limits of polynomial and rational functions. So first we're going to write some preconditions. We're going to let a, c, l, and k be real numbers. So this means element of the real numbers. And the limit of our function f as x approaches a is going to equal L. And the limit of our function g as x approaches a is going to equal k. Now, first rule, sum and difference rule. If we have the limit of two functions that are being added or subtracted as x approaches some value, then the value of the limit of those sum and difference is just equal to the sum or difference of the limits as if we treated them individually. The product rule tells us that if we take the limit of two functions being multiplied together, then the limit of the product is equal to the product of the limits. Constant multiple tells us if we have a function being multiplied by a constant, we can evaluate the limit of that function individually, which in this case we determined was L, and just multiply it by that constant that the function's being multiplied by. Quotient. If we have the quotient of two functions in which we need to determine the limit, we can determine the limit of each function individually and take the quotient of their limits, as long as the limit of the denominator is not equal to 0. And lastly, the power rule. If we have to take the limit of a function raised to some power, we'll do a rational to consider all possibilities, then this will equal the limit raised to that same exponent, as long as this answer is an element. I'll just say the whole thing. I won't rewrite it. So as long as this answer is also a real number, and the way that's going to be a real number is if the following is true. L needs to be a non-negative number if we have a scenario where S is even. So just a quick recap. When we have rational exponents, the denominator dictates what type of radical you're dealing with. So if we have an even index radical, say a square root, if L happened to be a negative number, well, then we would not have a real number here, right? That would turn into an imaginary complex number. So in the event that we have an even index radical, we just need to put this condition on here that L needs to be non-negative. So how are we going to determine limits of polynomial and rational expressions using just these properties? Well, let's say we have the limit, we'll just do a quick example, of x squared plus x minus 2 over x plus 4. And we want to do as x approaches 2. Okay, up top, we can see that we have three things going on. We have x squared plus x minus 2. So we have, between these two pieces, we have a sum. And between, once we establish that, with whatever that is, we'll have a difference with what the last term is. And on the bottom, we just have a sum. Then once we clean up both the top and bottom individually, we have a quotient to deal with. Okay, so we have all of these properties that we can utilize. And within that first sum, we have a variable raised to an exponent. So we can utilize that power rule before we even start that sum. And within all of this, you should notice that each piece is some portion of that identity function that we dealt with initially and the constant function. So we just have constants and identities with a bunch of different rules attached to them. So if we looked at the x squared piece first, what is the limit of x squared as x approaches 2? Well, based on my power rule, I can just plug in 2 to that x and just raise it to that exponent after. So from that first piece, we'll get that the x squared portion is 4. And then we're going to add that. Well, what is the limit of the identity function? So actually, let me do this in a different color. So the first piece, x squared, is 4. Now, what happens when I'm looking at this piece? Well, the limit of x, the identity function, is just whatever x is approaching. So it's going to be 2. And then the limit of a constant at the end is negative 2. Well, the limit of a constant is just whatever the constant value is. And then, based on our sum and difference rules, again, the limit of a sum or difference is equal to the sum or difference of the limits. So we can just clean this up with basic arithmetic, and we'll reveal that the numerator is just 4. Now, what about the denominator? Well, let's look at this. We just have x. Again, the limit of just the identity function as x approaches some number is whatever the number x is approaching. With it in this problem is 2. So we'll just put a 2. And then we have this piece 4 here. That's a constant function. So the limit of a constant function is just the value of whatever the constant is. So we'll have 2 plus 4. And we have a sum on the bottom. So again, the limit of a sum is equal to the sum of the limits. So we'll have 6. We can clean up this ratio. So the limit is 2/3. Now, that may seem overwhelming. Do you have to do this every time you're trying to evaluate a limit? And the answer is no. What you could notice is that essentially all we did was directly substitute 2 into all of the pieces that were a variable. And that is exactly how you evaluate limits algebraically. So let's establish that. The major takeaway from this video is when you evaluate limits algebraically, you are using direct substitution. And the great news is that while we were establishing a way to evaluate polynomial in rational functions, this actually carries over and can be utilized for polynomials, rationals, but also exponentials, logarithms, and trigonometric functions. when evaluating a limit. So our first move every time we have a limit question in this class that we need to determine algebraically, the first thing I want you to do is jump to direct substitution. And as a result of that direct substitution, we could see a few possibilities. So when we have the limit of a function as x approaches a, what we're going to do to determine that limit is just plug in a to the function. If this reveals the following, so possibilities for this, if f of a equals some number that equals the limit. Okay, so if we just get a number, then you're done. That's the limit. If f of a, now that's pretty straightforward, but we could have a rational scenario. So let's say when we do f of a with our rational scenario, we get a number over 0. This is going to be a does not exist. Okay, and then lastly, for now, what we could see is 0 over 0. This is indeterminate and requires more work. To determine the limit. The work you're going to do for now, we're actually going to have a tool for later in the course where if we have 0 over 0, a really nice, easy tool to actually evaluate the limit. But for now, with the tools that we have at our disposal, when we see 0 over 0, again, that's not a valid answer. It's not 0. When I say we need to do more work, what I want you to do is factor and cancel to simplify and reevaluate. So super quick example. Let's say we have the limit of x squared minus 4 over x plus 2 as x approaches negative 2. Through direct substitution, we'd get 0 over 0. That's not a valid answer. That's indeterminate, meaning I actually can't determine what the value of 0 over 0 is going to be. So if we factor and cancel, we'll see that the x plus 2's cancel, and all we're left with is the limit as x minus 2 as x approaches negative 2. We reevaluate through direct substitution, and it reveals that the limit is actually negative 4. So again, these last two scenarios that I presented, we'll actually section this off. These last two is going to be when we have a ratio or a quotient of two functions. Okay. We're going to look at these more specifically in a later video, which I'll cover indeterminate forms. But for now, just know if you get number over 0 does not exist. 0 over 0 is not a valid answer, and you're going to have to do more work. With what we have available to us right now, usually when we have rational expressions, what you're going to do is you're going to make factorizations, cancellations, so you can simplify the expression and then reevaluate. If we don't have a quotient of functions, like in this first example, and you just plug in, you get a number, well, that's the limit. And for whatever reason, some people think that 0 is not a valid answer. If you get 0 when you plug in, 0 is a valid answer for your limit. Okay. So that's where I will leave evaluating limits algebraically. Again, remember, your first move, direct substitution. If this third scenario appears where you get 0 over 0, we need to do more work. Otherwise, you can determine the limit through direct substitution.